All right, so let's get started with the second lecture today of CS 176B. Today we will be talking about the intellectual history of software-defined networking. So the learning objectives for today's lecture are why the networking was an intellectual failure and why it was hard to innovate in networking. And then what type of new abstractions did SDN propose that simplified controlling the network programs, and how some of these abstractions were realized, and what exactly is OpenFlow, which is always associated with software-defined networking. And before we jump into those details, let's try to recap what we learned in the last lecture. So we learned that software-defined networking is all about disaggregating or decoupling networks control and data planes. And it has three key components. One is the set of forwarding elements that are handling the packets. Then there is a network operating systems that communicates with these forwarding elements. And then the control programs that sit on top of the network operating system to control how exactly the packet should be handled in the data plane. Another view of software-defined networking or key component is the separation of control and the data plane. So the traditional view of network is a router, which is handling both the packet forwarding part, but also has this control part sitting at the top of the router, right? So think about a router where we have the brain of the routers sitting on top of the routing control platform itself, right? So compared to this traditional view, what changed is that all the control logic from the routers got to a remote control plane, and then the data plane was just handling packet forwarding, right? So this is the high level overview of what software-defined networking is, and that's what we covered in the class last week. Well, in the last lecture. All right. So now we will ask this question about why software-defined networking was required at the first place, right? Why do we need these set of abstractions where we have to separate the control and the data plane? Why do we need a network operating system? And other forwarding abstractions that were required or that are part of software-defined networking. So this class will be hinged upon the lecture that was delivered by Scott Shanker in 2011 at Open Networking Summit. Scott Shanker is one of the very famous researchers in networking community. He has published a lot, and you can check his Google Scholar to understand his impact on the networking area in general. But Scott Shanker, along with Nick McKeown at Stanford, were the two, the powerhouses pitching or evangelizing software-defined networking between the period of like 2006-7 all the way to 2013-14, right? So I said 2013-14 because by the time they already made the case and software-defined networking was getting mainstream, right? So this is a talk that is delivered in 2011. And this is a time when the idea of software-defined networking has been explored, has been shared with the community, but there has been limited adoption of software-defined networking. So this is an intellectual case that the Scott Shanker was making in that talk, and we will be using the key themes or like ideas that he presented in the talk. One thing that was very notable from his talk was that he said people who run networks, like in 2011, have to keep a superhuman amount of state in their head, right? And which means that the networks today are run by masters of complexity, right? And that was a very powerful statement, subtle but very powerful statement that was made, that running the networks today requires a superhuman effort, and we don't really have to do that, right? So this was kind of like the essence of his talk, and we'll cover that in greater details now. So first thing, the networking community should pat their back because internet was a success. Internet, like the public internet kind of like started around early 90s. And then when we're talking about, when this talk was delivered in 2011, it was and it is still considered a success, right? And the key to success was the abstraction of layers for networking, right? So, you can develop different type of applications, email, www, Skype, that can leverage a reliable or unreliable, sometimes the UDP transport. And then this TCP is built on a best effort global packet delivery, that is the IP. And then this IP is actually built on best effort local packet delivery like Ethernet, which is built on top of the physical transfer of bits through the copper or fiber or radio, right? So layering is very important and very critical for the success of internet, right? And this is something which you have probably covered in 176A as well. So why is layering important, right? So layering decomposes delivery into fundamental components. And then these components are independent but compatible, and they can innovate on their own, right? So the innovation of one layer is independent of the other, right? And as a result, it was an amazing success, right? But there's a but it was an academic failure. And now you might be wondering, as a networking professor, why am I saying that the concept of layering, the abstraction of layering that worked so well, that made internet such a huge success, why do we consider that as an academic failure? And the reason for that is that with that layering abstraction, what we built was an artifact. It was not a discipline, right? And peeking into the other areas out there which have been very successful in terms of being simple and easy to innovate and evolve, systems like operating systems, database systems, etc. When we teach operating systems or database systems, what do we teach? We teach students the basic principles of virtual memories and like the processes, right? So when we teach networking, we teach a bag of protocols. So bag of protocols, you learn those protocols. You learn TCP protocol, you learn IP protocol, you learn the HTTP protocol, DNS protocol. You run a lot of protocols. And then most of these systems, the operating systems or database systems, are relatively easy to manage, right? Because they have the right set of abstractions. So they hide away all the complexities, and managing those systems is relatively easy, right? In contrast, managing networks, even today, for the type of networks that have not really adapted software-defined networking principles, they're still notoriously difficult to manage. And as a result, the other systems continue to evolve, whereas networking evolves very slowly. So now you might be wondering that, okay, it's an artifact, it's not a discipline, it's really slow to evolve, but why? Why does networking lag behind? The simple reason is that networks were not designed for the level of complexity that we see right now, right? So networks, when we talk about networks used to be simple, think of ARPANET, where only 3 or 4 campus networks were supposed to be connected with each other. That was a very simple problem, very few hosts, very simple set of goals and tasks that everybody had that just connect these machines with each other, right? So that was supposed to be a very simple goal. But then over time, especially with the commercialization of the internet, new control requirements led to great complexity, right? So what is an example of this new control requirement, right? So one control requirement can be, and you read about border gateway protocol in 176A. So, a particular AS or a domain can have a choice about who they want to peer with and who they don't want to peer with, and what type of prefixes do they want to share with one type of peer, and what type of prefixes they want to share with some other type of peer, right? And what type of traffic they want to send over one link, what type of traffic they want to send over the other link. These are all control requirements that kept on evolving. Those requirements kept on coming as the commercial usage of internet grew, and that led to a huge amount of complexity. But the networking practitioners can pat their back, because fortunately, even in 2011 or even before software-defined networking was conceived, networks are always running. They had issues, they had downtime, but they were still more or less working, right? And they were working not because it was easy to make them work, but they were working because of the community's ability to master complexity, right? So the requirements came in, the complexity increased, but people just kept evolving evolving and evolving to master that complexity, right? And this ability to master complexity is a blessing. There is no doubt it's a blessing, but it is also a curse, right? And this is a very fundamental thing that missed in the networking discipline, that the concept of mastering complexity was always confused with extracting simplicity, right? So when you're trying to master something which is already complex, that is not really simplifying the problem. It is just reinforcing the complexity and laying ground for like more complexities in the future. And this distinction between mastering complexity and extracting simplicity for a particular problem are very different things, right? And this is something which Don Norman, who wrote multiple books on design principles, laid out. And that is something which Scott Shanker also used to make an intellectual argument for software-defined networking, right? So far, what are your takeaways? The takeaways are that networking focused on mastering complexity, and it gave little emphasis on extracting simplicity from control plane, right? So it was all about mastering the complexity. Your new requirements kept coming in for the control plane. Everybody just focused on mastering those complexities over time, right? But software-defined networking, in contrast, focuses on extracting simplicity, right? And in principle, it sounds very easy. Or when I look at things in retrospective, yeah, it's such an obvious thing. Why are we continuing to master the complexity? Why just we extract simplicity for the problems? It's not as easy as it sounds, especially when you are at the moment when all you see around is everybody blindly focusing on the idea of mastering complexity, right? There was some bravado associated with how much complexity can you handle and master. I think that kind of like created an environment where coming up with these ideas was not a very straightforward or a trivial thing, right? So we know that there are other disciplines that have done a great job in extracting simplicity. So are there any lessons that we can get from those areas, right? So how did other disciplines focused on extracting simplicity? If we understand that, maybe we can understand how we can apply similar principles for the networking area as well. So let's consider the example of programming, right? So when programming started, say in 50s and 40s, maybe 50s, 60s, right? I might be wrong here. So everybody was focused on the machine languages, right? There was no abstraction. And the only skill that you required to excel was your ability to master complexity, right? It was a very, very crucial skill. And then over time, we had some higher level languages. We had the operating systems and the other related abstractions. We had file system, virtual memory, abstract data types, etc. Right? So that definitely helped in terms of the simplicity with which you can write programs, right? And then we have modern languages which provide even more abstractions. You don't really worry about all the nitty-gritty details of the mechanisms. And you have the principles of object-oriented programming. You have garbage collection, right? What is common across this evolution of programming is that over time, better and better abstractions kept coming, right? And with those abstractions, the intent or what you really want to do or want to make a program do was separate from how it will make it work, right? So those abstractions hide away the lower level details, and that helps with the evolution of the area in general, right? So what is the key takeaway from this journey of or evolution of programming is that for simplicity or for extracting simplicity, abstraction is the key, right? And this is something which, Barbara Liskov famously quoted in her Turing Award talk, that modularity based on abstraction is the way things are done and should be done, right? So now you might be wondering that, hey, we're talking about 2006, networking kind of like started in 1976. So for 30 years, didn't we have any abstraction networking, right? So I will be dishonest if I say there was no abstraction in networking. There was an abstraction. It was a great success. That was layers that we just read, right? So layers are great abstractions, but they only deal with the data plane, right? So when I say that they only deal with the data plane, what is layer, right? So we have these layers of application, then transport, then network, then the link layer. So all these layers are talking about providing abstractions for how to handle the packet, right? So that is just a forwarding abstraction or the data plane abstraction. But networking lacked powerful abstractions for the control programs, right? Or the control plane, that how exactly these routers should be configured, what exact forwarding rule they should be applying on the packet. That is all part of the decision making that the control plane has to do. Or think about the brain of the network, right? And for the brain of the network, there was not any powerful abstraction. The powerful abstraction which is layering is only for how the packet should traverse the network, right? And that kind of like created all the challenges for networking. Uh, so in principle, I think there was an abstraction which was very, very successful, but it didn't really help with the evolution of networking, right? So now the question is, okay, we need better abstractions. How do we find those abstractions? So before we try to explore how we find those abstractions, let's try to first explore the network control program or the brain of the network problem in much more detail, right? So let's use the example of a routing control protocol, right? So you might or might not be familiar with this protocol called Open Shortest Path First, right? So this is an internal gateway protocol, or IGP, which basically decides that how should a network or how should a packet traverse within a particular network, right? So think about say AT&T. So within AT&T, how a particular packet should go from point A to point B will be decided by Open Shortest Path First Protocol, or OSPF, right? So it is a routing protocol. It is specified in RFC. And I think the version 2 is what RFC 2328 is all about. And that is 245 pages of specification, right? So as you can, like when I say 245 pages of specifications, that kind of like already is intimidating if I want to make any changes to this type of protocol, right? But what are these 245 pages talking about? There are two key components in the OSPF specification. One that talks about how network can build a consistent up-to-date map of the network, right? And it spends 101 pages talking about how that goal can be achieved, right? And then the second part, which is most important from the control perspective, is the Dijkstra algorithm that decides the open, or that selects the the shortest path first, that operates on the map, and that is specified with just 4 pages in the specifications, right? So this gives you a sense of the actual goal is to decide the shortest path, but to achieve that, because the control sits on the router itself, so all these routers have to coordinate with each other so that they can build this consistent up-to-date map of the network, and that takes 101 pages of specification, right? So this mechanism of how the network control problem can be solved, there is a mixing of the intent and how those intents can be achieved, the mechanism that enable that intent, all that is mixed in the control plane problem, with OSPF. So OSPF is actually a very good example, of this type of routing protocol is a very good example that how can we extract simplicity here, right? So how can we simplify network control? One requirement is that they should be able to operate without communication guarantees. Why was this requirement? Because we had this need for these routers to coordinate with each other, and some links can go down. Then there were all these complex mechanisms about how they can maintain that consistent state of the network, even though there are no communication guarantees, or some communication guarantees are missing, right? So the abstractions that can enable this simplification is the distributed state, right? So the fact is that all these routers have some distributed view of the network, and the achievement, or the goal should be that we should develop an abstraction that simplifies this distributed state, right? The second requirement is that it needs to compute the configuration for each physical device, right? So all these routers need to compute the configuration that should be applied, the forwarding plane configuration that should be applied on each of those devices. So what we definitely need is a simpler data model for network configurations, right? And the third requirement is that these control protocols should operate within the network level protocol, right? Like whatever new thing that we come up with, it has to comply with the network level protocol that have already been, accepted or adopted by these routers, right? And to counter that, the abstraction that we really need is a general forwarding model, right? A forwarding model that is not tied to a specific type of device protocol or something, right? So it's something which is very generic, agnostic to agnostic to vendors that are making these devices. So let's start with the first abstraction, which is the distributed state abstraction, right? And this distributed state abstraction is required such that we can shield the mechanisms from the vagaries of distributed state, right? So we want the control programs to have access to the state of like, what different routers are seeing, but we don't really want these control programs to worry about the mechanisms about how that can be achieved, right? So that detail has to be abstracted away or hidden away when we are thinking about the control programs, right? So think about the Dijkstra. When we talk about the Dijkstra algorithm that has to be applied, all it needs is a map. How that map can be generated is something that should be abstracted away, right? So here, I guess like a natural abstraction is a global network view, right? As long as the control programs have access to this global network view, which is, think of as an annotated network graph with some APIs that the control program has access to. With that type of natural abstraction, the mechanisms of how that global network view is enabled is just hidden away, right? And the control mechanism is now a program that uses these graph APIs to decide how or what type of decisions it should make, right? So now we are replacing this distributed protocol, which is all about how these nodes should coordinate with each other, with a graph algorithm that has a consistent view of the network, and it applies a control program on that graph, right? So this is very different from how networking was done earlier, right? As I was saying, like, those two mechanisms and abstractions were kind of like mixed together, and every router was doing the same thing, and that just added the complexity to the process. So next abstraction is the specification abstraction, that when we think about these control programs, so the control programs should be able to express the goal or the desired behavior that they want the network to do, right? So it should not be responsible. When we think about the control programs, they should not be responsible for implementing that behavior. And this is very important, right? So in the previous discussion that we had for OSPF, the ability for each of those networks to have an up-to-date or consistent map of the network was a mechanism, right? So the control program should be decoupled from this type of mechanism, right? It should just focus on what is its intent, what type of desire does it, or what type of behavior does it want to exhibit, and just write or write how that behavior can be extracted, right? Not about how that behavior will be implemented, right? So intent and mechanisms have to be separated from each other. And the natural abstraction is that we provide some simplified model of the network such that this simplification only focuses on the details that are required to specify the goal, not how it can achieve it, right? So, like a simplified abstract view of the network such that those control programs don't have to worry about other things in the network, right? And this is exactly what is achieved by the principle of network virtualization, right? So network virtualization is abstracting away different vagaries of the networks and then focus on a subset of the network, which is of interest for the control program, right? And then the third abstraction is the forwarding abstraction. So control plane needs a flexible forwarding model, right? So when we have a control plane, it needs to decide a certain set of actions for the data plane, right? So it needs a flexible forwarding model that it can operate on. And then those abstractions that are provided, the forwarding abstraction, should not constrain the control program itself. So it should be able to support whatever forwarding behaviors that is needed, right? So there should be no constraints to the control program in terms of how the forwarding can be done. And it should, very importantly, hide the details of the underlying hardware, right? So this is very, very crucial for evolving these systems beyond vendor-specific solutions. And I think like this is something which is hard to appreciate without understanding that in 2006, 2007, when we're talking about the networking was dominated by just one or two players, right? So everything about networking was dictated by companies like Cisco, Juniper, and maybe to some extent Alcatel, right? So these were the dominant networking players, and going beyond these vendor-specific solutions was very, very hard. So this point about that the forwarding abstraction should be agnostic to the vendors is very, very critical, right? So now to summarize what we learned so far, the question that we started to answer was why software-defined networking? And the answer is that, like the focus so far was to master complexity. But in the longer run of things, like mastering complexity is unsustainable. And that's why we needed something to extract simplicity for control plane. software-defined networking is capable of extracting simplicity. It does so by finding the right abstractions. And the three abstractions that software-defined networking focuses on is the distributed state, the specification abstraction, and forwarding abstraction, right? So this is, in some sense, how software-defined, like why do we need software-defined networking? Why do we need to extract simplicity? How software-defined networking extracts simplicity, right? So we have answered those questions so far. One important question that we still need to answer is that how these abstractions can actually be enabled, right? So how are we going to realize these SDN abstractions? So let's go by one abstraction at a time, starting with the data distributed state abstraction. So the core challenge in distributed state abstraction, realizing distributed state abstraction, is that we need to make this distributed control problem, like this is a distributed control problem because you have to make decisions at router A, router B, router C. So that's a distributed control problem, but we have to logically centralize it, right? So that we don't have to worry about the mechanisms about how a router A is going to know what router B sees and router C knows what router D sees. Like those challenges, those mechanisms have to be abstracted away. So the control program should only be working as if there is one big switch or one big routing network or router that it has to operate on, right? So that's kind of like the idea of logically centralized abstraction. And how it can do so? It can do so by building a layer that can gather information from network elements, irrespective of what control program we are running, and it is capable of disseminating control commands to the network elements, right? So in short, what that means is that we need to develop a network operating system that provides mechanisms and interfaces such that we can talk to these forwarding elements, gather information, create a centralized view of the network, and then once the control program makes some decision, it disseminates those control commands to the network elements, right? So the control program is working on an abstract view or a like global logically centralized view of the network, and it is not worried about the mechanisms, right? So the mechanisms are taken care by a network operating system, right? So let's try to visualize that a bit more. So how can network operating system provide this distributed state abstraction? We have these forwarding elements, and then the network operating system kind of like sits at the top of these elements, and then it collects the information from them, creates a global view, provides that global view to the control program, and then control program makes some decisions, and then network operating system sends them back as the commands for these devices, right? So that is the distributed state abstraction. Now let's talk about the specification abstraction, right? So what is a specification abstraction? Or how a specification abstraction can be realized? Abstraction here is that we need a simplified model of the network, right? Because when we are trying to specify what the network needs to achieve, it needs to specify the desired behavior. And for that, it needs to abstract away all the details about other portions of the network that are not relevant to the problem, right? So we need a simplified model of the network. The control program then will merely configure that abstract model. Rather than working on an actual network topology, it can work on an abstract topology or the abstract model of the network, right? And then compute these configurations, which are also abstract in nature. And then it will require a shared control layer that translates, makes these translations. So an actual network view to an abstract network view, and then abstract configuration to an actual network configuration, right? So that translation has to happen with some shared control layer. And that control layer is called the network virtualization layer, right? So in this case, you have the network operating system, it has the actual view of the network, and then we have a virtualization layer that provides an abstract view of the network. Then these control programs operate on the abstract view, the control program A will work on, say, the 3-node graph, the control B will work on this other 3-node graph, and then they will write down the abstract configurations, and then the virtualization layer is going to translate that into some actual configurations which will get pushed into these devices, right? So now the third abstraction is the forwarding abstraction. So as we know that switches have two brains, right? One is the management CPU, which is very smart because it is capable of doing general purpose computing, but it is slow. And then we have the forwarding ASIC, which is very, very fast, but it is dumb because it can only do a certain set of operations, right? And we need a forwarding abstraction for both these things, but the CPU abstraction can be anything because it is a general purpose computer, right? The ASIC abstraction is a bit more subtle, because it has a lot of constraints, right? So it has constraints in terms of what type of packet processing it can do. So OpenFlow is an instantiation of the forwarding abstraction, right? So as I mentioned at the start of the lecture, that OpenFlow has always been associated with software-defined networking, but it is very important to differentiate OpenFlow and software-defined networking. Software-defined networking are a bunch of abstractions that help extract simplicity for network control plane, but OpenFlow is just an instantiation of one of those abstractions, which is the forwarding abstraction, right? So now we are going to dig a bit deeper into the OpenFlow, what is OpenFlow, and how it enables the forwarding abstraction. All right, so let's talk about OpenFlow. As I mentioned earlier, that OpenFlow is an instantiation of the forwarding abstraction for software-defined networking. The basics of OpenFlow are that you have a control program, you have a network operating system. The network operating system needs set of APIs or interfaces so that it can talk to the forwarding element, right? So OpenFlow protocol provides those interfaces. It provides this it basically provides the set of protocols that the operating system can use, and then it has this small daemon sitting on the switch which manages or handles the messages received by the operating system and then sends those messages also up to the operating system, right? So what are the set of commands that the network operating system can send to the forwarding element? Those will be sent as bunch of OpenFlow rules, or we will cover that, like those are a bunch of match action table rules. Those rules can be that, hey, if the header of the packet is P, then send this packet to port 4, right? So it is matching on a particular header, and then it is taking an action to send that traffic to port 4, right? Similarly, if the header is Q, then override the header. That is, the action will be to modify the header and then add another header to it and then send it to two different ports, right? So it has a forwarding action, it has a write action to the header, right? And then a rule can be that, hey, if you see a header that I don't have a role for, you just send that packet to me, to a control program, which will be sitting in the user space, and then it can handle those unknown headers as well, or like for the packets that we don't have a role for. So the plumbing primitives here, like there are two basic things. One is the match part, which matches on the portions of the headers, and then there is the action part, which is operating on the headers in terms of writing the header fields, masking it, pushing it, popping it, or forwarding it to a specific port or a controller, right? So when we say match, those match fields are applied on arbitrary combinations of bits in the headers, and it can match on any header or any new header, and it allows any flow level granularity, right? So when we talk about the match here, I think we need to talk a bit about the flow space abstraction. That flow space abstraction is that when we have the header is a combination of different layers based on the data plane layers that we have. So we have Ethernet, we have within Ethernet, we have the IP, within IP, we have TCP, right? So the flow space can be defined technically by any collection of these bits, right? So this is the normal headers, but you can have a user-defined flow space as well. And so just to be clear, so OpenFlow 2.0 enabled a very abstract or arbitrary combination of these bits, but before OpenFlow 2.0, in OpenFlow 1, the type of combinations of bits that you can use to define a particular match rule were dictated by these existing set of protocols, right? So flow space, as a simple example, if on the x-axis I have the IP addresses and then IP source address, and on the y-axis I have the IP destination address, then a single flow can be represented by a particular point, which is combination of these IP addresses, source and destination. Like all flows that are coming from an IP address A can be represented by this line, and then all flows that are between two subnets of or range of IP addresses, source IP address and destination IP address, can be represented by a rectangle or a square shape, right? If we try to go a bit more generalized, if we generalize this flow space abstraction, we don't have to limit ourselves to just the IP addresses. Those fields that we are trying to use to define the dimensions of this flow space can be anything. It can be a combination of the 5 tuples or 13 tuples that we see in the packet headers, right? So, a single flow can be a point, and then a set of flows can be any arbitrary shape in this multidimensional flow space, right? So there are some properties of these flow spaces that are important from networking perspective. One, they offer backward compatibility, that the current layers that we have in the packet, there are special case. In the future we can replace them with something else, and then develop we will still be able to extract those arbitrary combinations of bits to define flow spaces. So what we have with the existing layers, and when I say existing layers, think about the Ethernet, IP, and TCP. So those are a special case of what is possible within the flow space, right? But technically a flow space can be any arbitrary combination of the bits that you have in the headers, right? So if we want to change anything, like the endpoints don't need to change much, like all these changes can be enabled by changing how we read those bits in these network devices, right? And these flow space abstractions, the match action tables, are easily implemented in hardware. So from hardware perspective, the technology already evolved that how we can do we can use this TCAM to match on arbitrary combinations of bit fields in a particular space, right? And then it also provides the strong isolation that the geometrical shapes that we were talking about that represent a group of flows like in a flow space that actually one, like their simple geometric construction enable one easy visualization, but it also help with the verification problems that we envision for networking, right? So if you want to verify the behavior of a particular network, given these properties that the flow spaces exhibit, that becomes very, very easy, right? And that's something that I personally explored in one of the research papers that I wrote, that if I want to write a logic of authorization of a flow space, right? Like, so who is the owner of a particular flow space? Given the awesome properties like the disjointness properties that are offered by the flow spaces, I think that was very, very helpful in building the abstractions and the mechanisms of enabling authorization for the flow spaces, right? So let's try to understand how match action forwarding abstraction works. So a packet header is coming in and the header is H. And if I have a rule which says like, if the header is H, or like if the fields in the headers are kind of like matching to H, then there is an action that is specified. You apply that head like action, which translates the header to H prime and then sends that traffic, right? It is possible that those action primitives can be that you forward to a set of ports, you push header after bit 12, you pop the header between bit 8 to 12, decrement bits 13 to 12, drop packets. So these are all actions that are possible, or these are all like the wide range of actions that are possible once there is a match. And this is something that you can specify in the match action table in the data plane using OpenFlow. And think these are all the plumbing primitives, and at a high level we can think of OpenFlow as a direct implementation of a match action model of processing, right? So this model easily captures the current switches such as the Ethernet switches and the IP routers and the MPLS switches that are already out there. And if there are multiple layers of protocols handled in box, it's easier to think of that as a sequence of tables, right? So if you want to apply, you want to do certain set of actions for Ethernet layer, then certain set of actions for the network layer, then for the TCP layer, then those can be thought of as like composition of different tables applied in sequence, right? So for example, if there is a packet that is coming in and like one layer is H1 and the other layer of the header is HN, then you first apply the match action table, like you match on H1 and then apply action H, and then on the next set of fields that you have, you can like match on H and then apply the next set of actions, right? So the protocol is each protocol is processed in this case in its own table. And the first table in this case can be the VLAN, right? And the second table can be something for the access control that like the firewall policies that need to be implemented, right? All right. So, sorry. So I think like given that we have journeyed all the intellectual journey of the software-defined networking, right from where it was failing, what it really needed, what lessons we could learn from the other areas, and the three abstractions, and within those three abstractions, the specific open flow protocol that was critical for the evolution of software-defined networking and kind of like helped help make software-defined networking become a bit mainstream, right? But I also want to give a bit of a historical perspective that the ideas of software-defined networking came out around in 2008, but before that there was a lot of effort going on in the networking community. So it will be incorrect to say that nobody was thinking about these abstractions. They were not really as principled as software-defined networking is right now, or there was some lack of clarity in terms of how exactly future should look like. But there were a lot of solutions, and 2003 to 2007 was a very interesting time in the networking community where new networking management paradigms were defined, right? So routing control platform, which was developed at AT&T, and also there was this like a follow-up called 4D, which was talking about four dimensions of how network management should be done. And Ethane is something that you already read in the last class, which was talking about enabling flexible control for the enterprise network, right? So this all happened in these 3 or 4 years. That was very exciting time for networking. And then in 2008, like a big burst of software-defined networking, like a lot of clarity came out for software-defined networking with the development of a network operating system called NOx, and the forwarding abstraction, like in a real instantiation of the forwarding abstraction with the open flow protocol, right? So most of this work kind of like happened at Stanford, and this led to creation of a company called Nicira. Nicira was acquired eventually by VMware for a couple of $billions. So right, it was very, very successful. It was kind of like gratification of a networking principle, something like people conceptualized, then developed, instantiated, and then created a startup out of it. Very Stanford thing to do, and then that was acquired by VMware. So between 2008 to 2011, the community was figuring out, okay, there has been some success, but like, how do you channel it such that this is not a blip, it becomes a more sustained movement. So I think like in 2011, Open Networking Foundation was created. Most of the content providers and cloud service providers were the board members for Open Networking Foundation. Companies like Google, Yahoo, Verizon, Microsoft, everybody who saw huge dollar savings with software-defined networking was part of Open Networking Foundation. Companies like Cisco and Juniper were initially resistant and hesitant to join this bandwagon of software-defined networking, but they eventually realized that like they also have a lot to gain if they embrace the principles of software-defined networking, right? And they kind of like realized that those days where they were the dominant players in the market and they could dictate whatever needs to be done in networking, those days were gone. So they quickly adopted, and I think like these days Cisco and Juniper and all these other companies who were like leaders of networking in their heydays, I think now they also offered products that support principles of software-defined networking. And something very critical happened in 2013. It was the development of a protocol independent switch architecture, PISA, which was in some sense evolution of the open flow instantiation. So it was a new instantiation which embraced all the principles that we were talking about, or at least were envisioned with the initial version of open flow, that we should be able to match on any arbitrary combinations of the packet header fields, and then we should be able to do some complex computation on these fields within the data plane itself. So that led to this architecture called PISA, which is Protocol Independent Switch Architecture. And one instantiation of that was RMT, which was reconfigurable match action tables, right? So what we read about earlier was a match action table, but those were fixed functions. So, like the type of matches, the type of actions were kind of like fixed, but reconfigurable was that you can reconfigure what type of actions you want to take within the same hardware instant over time, right? So we will cover RMT in greater details in next few lectures. But I just wanted to give an overview of like, okay, we studied OpenFlow. It's just a small part of the bigger story. There was a lot of effort going on in the networking community, but it was critical, but it is still, just one instance of good idea getting instantiated, right? So now that brings us to the end of this lecture, and some of the takeaways that we have from this lecture are that the layering abstraction that we developed for networking was a great idea, but it only works for data plane. So that didn't help with the management or handling of the increasing complexity for control plane. And before SDN, the networking focused on mastering the complexity, but we learned that mastering complexity is very different from extracting simplicity. And this was actually the goal of software-defined networking. Software-defined networking focuses on extracting simplicity by developing three core principles. One is about enabling distributed state, then providing some specification abstraction with network virtualization, and then forwarding abstraction. And OpenFlow was one initial instantiation of that idea, right? So with that, I will end this lecture, and I hope you learned a lot about the intellectual history of software-defined networking, and now you are able to appreciate why we have those, those figures for software-defined networking, where we have some dumb forwarding elements, we have some network operating system, we have a virtualization layer, and then the control programs that operate on that virtualization layer. So in the next lecture, we will dig a bit deeper into network virtualization. We will talk about FlowWiser, and we will talk about the software program that was developed by Nicira, which was acquired eventually by VMware. All right, I hope you have fun with this lecture. Thank you.